All right, good morning, everyone. Are you all able to see my screen? Anyone is able to see my screen? Yeah, okay, thank you. All right, so last time we were discussing flow models and we started to scratch the surface of flow models. And the way in which we built up the story is autoregressive models. For autoregressive models, we can easily access the likelihood because using the chain rule. Uh, However, there is one problem with, in fact, two problems with autoregressive model. The first problem is that there is no latent variable representation. And the second problem is that, as you know, and they are sequential in nature when we are sampling, similar to what the LLMs do. Okay, because autoregressive models are nothing but LLMs. Okay, or vice versa. LLMs are autoregressive models. And we saw the other type of model where we saw the VAs. In VAs, we saw that we were able to find the latent variables or the latent features, latent representations. But then it came along with a problem that the likelihood is not accessible, and it became a pain to train the model because we had to take the access of the lower bound, which is elbow, and then so on and so forth. Okay. And now we wanted to see if by design anything we can do, which basically can take Z and map it to a X. All right. Or take X and map it to a Z and vice versa. It's an invertible mapping. And, and those invertible mappings were achieved via the change of formula, change of variable formula. Okay. And these were essentially deterministic invertible transformations. And the problem only problem with those transformation is that yes, they are deterministic in nature because every X will map to every Z, one Z only. So there is a one-to-one mapping. The other problem is that the dimension of Z and X are same, and because it is invertible in nature. And ideally, in any sort of latent representation that we want to do, we want compactness of Z so that it becomes, so that basically it is able to capture the latent representation better. Okay. Now, and the last thing that we saw there was essentially that the change of variable formula is essentially um, you cannot do a direct change of variable. You have to add a normalizing constant. That normalizing constant was basically the determinant of the matrix. And in multi variate flows, it became the determinant of the Jacobian of the inverse transformation. Okay. Now that's where we left the discussion, and this slide is essentially talking about talking about the same thing. So consider a directed latent variable model over observed variables X and latent variables Z. In normalizing flow models, the mapping between Z and X is given by this F theta, which is nothing but a neural network, and theta are the parameters of the neural network. This thing we talked about that, I mean, X and Z have the same dimensions. They are deterministic and invertible, and this is basically the functional form. And obviously, since it is invertible, we can write it like this. And this is essentially the representation of this. Okay. And using the change of variable formula, we can easily calculate the marginal likelihood of P of X, which is essentially given by this particular change of variable formula, which is P of X at Z is equal to, P of X at X is equal to P of Z at F. And the inverse mapping of X. And then it is the determinant of the Jacobian of the inverse mapping. The only thing that we need to be careful about is this entire normalizing flow model is based on continuous data. It is not applicable for what you call discrete data. For discrete data, we have some other methodology. But this particular entire machinery is only applicable for the continuous stuff. Okay. So the good thing that you should take out from this slide is likelihood is tractable in this particular case. And the limitation is that X and Z are continuous, and obviously X and Z have the same dimension. Okay. Now let's talk through it a little bit more. Now, actually, how do we actually design these flows? The way in which we design these flows is essentially that the change first is normalizing. So the change of variable gives us a normalized density after applying an invertible function. Okay. And it is called flow because and what we do in neural networks, this is obviously a neural network. What we do in neural network, we stack up various layers, right? Here also we stack up multiple transformations. So if you can see, we pick Z, 0. Okay. We pass it through an invertible function f theta. Then there are multiple all functions which are here, and that particular brings it to z of m. And z of m is nothing, but this is actually x. All right. So this is the final x that is there. Okay. So what we are doing is, in the previous slides, what we were telling is essentially we talked about only a one component, which was one uh, um, invertible function. But when you are actually designing the flow models, what you have to do is you have to stack up multiple functions and multiple invertible functions to basically come up with a more complex distribution. So what happens essentially is that combining relatively simple building blocks to essentially what we are doing is essentially combining relatively simple building blocks to basically build complex and flexible architectures. That's what we are doing. Okay. And what we do is, as I have told you, we start with a simple distribution x0. It is Gaussian, and apply a sequence of m invertible transformation to finally obtain x is equal to z of m. And then, and basically by change of variable formula, we know that this change of variable formula now is only difference in the change of variable formula is basically this product term, because now there are multiple what you call layers. So it is the product of the determinant of the Jacobian of the inverse transformation. Okay. And one thing you need to know is that parameters of each of these layers is going to be different. And theta, when we say theta here, theta is nothing but a union of all the parameters. Okay. So this is what is the core concept for the flow models. So what we are doing is we are taking invertible functions and we are stacking them together and then using the change of variable formula to basically get access to the likelihood and train the model. Now, this is exactly what we are doing here. And this is just a simple visual representation. These are called the planar flows. And planar flows essentially transforms, into transformation on map, and it maps point from 2D plane to another basically. So see this particular thing, what happens? We start with a unit Gaussian Z0, and then we apply one transformation and it becomes a little bit more complex. And then as we make multiple transformation, this really becomes a complex structure, which essentially is what we want. Similarly, for a uniform distribution, and we can do the same thing. So what this is trying to depict is, you have multiple, you do 10 planar transformation. 10 planar transformation can transform simple distributions into more complex one. So it is not a one jump that we are doing from Z to X. We are applying multiple simple transformations to ultimately get a complicated distribution. Okay. Now, what we know here what we know here is, so overall, what do we need? We need only two things. All right. The first thing that we need is essentially we need to do two things. First is parameterize the mapping. Okay. And number two, this is one. Okay. Number two is we need to do learning. Okay. We need to do learning. Now, the question that comes to is how do we do the learning? And obviously, if to do the learning, you need to do the maximum log likelihood over the entire data set. And if you apply, I mean, so likelihood is easy in this particular case because what is maximum log likelihood? Maximum log likelihood is equal to this plus this. We have just taken the product and converted into sum because there is a log. Okay, and pick theta that maximizes the log probability of the data. That's what we are doing. Okay, so we can get exact likelihood evaluation via the inverse transformation, that is x to z, and change of variable formula, and sampling via the forward transformation, which is this. Okay, and latent representation inferred via inverse transformation, no inference network required. So what it is trying to say is that if you learn f theta, you can easily infer f inverse theta. Okay, or vice versa. So you can choose what you want to learn, but if you learn one, you don't need to learn the other. Okay, so no separate encoder, no separate encoder needed like VAE, only mapping needs to be inverted. So that's essentially the story. Okay, now the question on that comes here is, now what are the key ideas? Now we have talked a lot about the machinery, but what are the key ideas that we have talked about and how do we achieve it? So the first thing is that we need a simple prior that allows us efficient sampling and tractable likelihood. So for example, isotropic Gaussian. Isotropic Gaussian is nothing but a d-dimensional Gaussian, and which is essentially written like this. Okay, which is essentially, it's a d-dimensional Gaussian. And so now, so we start with a very simple distribution of P of Z because we want to easily sample from it, and we want a tractable likelihood. Invertible, we also need invertible transformations with tractable evaluation. So likelihood evaluation requires effective evaluation of X to Z mapping. Sampling requires the reverse. Okay. Now, in this whole formula that you have seen, one thing that it is fine. We'll learn a neural network of all these particular things and all. But one thing that you see here is we would need to learn we would need to calculate the determinant of the Jacobian. Okay. And that is one thing that we need to solve for. Now, computing the likelihood also requires the evaluation of the determinants of a n by n Jacobian matrix. So Jacobian matrix are typically n by n, right? So if you have n dimensions, it will be a n by n Jacobian matrix, right? So even if you have 100 dimensions, it is going to be 100 by 100 Jacobian matrix, which is quite big. And it is computationally very expensive to calculate those Jacobian matrices. So can we use some trick here? Okay, so the trick that we are going to use here is we need to come up with a special structure of the Jacobian matrix that will help us reduce the computation. Okay. Now, what is the special structure? The special structure is the determinant of a triangular matrix is the product of the diagonal entities. Okay. What we need to do is we need to convert the full Jacobian matrix into a triangular Jacobian matrix. And you know, in a triangular Jacobian matrix, there are lots of zeros. It can be upper triangular matrix. It can be lower triangular matrix. So there are lots of zeros in the triangular matrix, and that makes computation very uh, efficient. Okay, how do we achieve this particular thing? The way in which we will achieve this particular thing is so first try to get a visualization of this. So what are we trying to do? We are trying to calculate the Jacobian matrix. And what does a Jacobian matrix do? A Jacobian calculates basically the gradient of each output with respect to each input. So if there are n inputs, okay, so it will be a n by n Jacobian matrix because you will have to calculate the what you call each gradient of each input output with respect to each input. So now how can you make this Jacobian triangular? Okay, how can you make this Jacobian triangular? You can make this Jacobian triangular by making this, by introducing some dependencies here, conditional dependencies. Okay, so you can make it what you call um, you can convert it into a lower triangle or an upper triangle if you introduce some dependencies. And what kind of dependencies, conditional dependencies they are? So if you want to make it a lower triangular matrix, so in case of a lower triangular matrix, everything above the triangle is zero. Okay, how do you achieve the lower triangular matrix? You achieve the lower triangular matrix, and this is only possible if the ith output depends only on the previous inputs, same as the autoregressive case. Okay, now what has happened now? You see that none of these particular things here, which are here, they are all zero because they don't they all they are not dependent, and I mean on the previous one. Okay, so what can we do now? Now if we make this particular thing lower triangular, or I mean there are some research which are there in as a upper triangular matrix as well, where you can make your subsequent and outputs dependent on the current one. Okay. Now the question is, what do we achieve by this? What we achieve by this is the determinant can be computed basically by multiplying the diagonals of a Jacobian, diagonal entries of a Jacobian. Okay. Now how can we do it, and how do we achieve it? Let's talk through it a little bit, right? So sorry. Okay, so there are various designs which have been done in this particular case in terms of how to achieve this. Okay, and we will go through a few designs. All right, we will go through a few designs, and then we will see where we go from there. Okay, architectures basically. So the first architecture that we'll go through is NICE, which is additive NICE, or the additive coupling layers. And let me explain you it in a very simple manner. Okay. So we want, this is the forward transformation x to z, sorry, z to x. What we do is, the first thing that we do is we take the z's and we create two disjointed subsets. It does not have to be equal. So if there are 10 z's, we will make two equal subsets of 0 to 5, and then 6 to 10, or any of permutation combinations would work. Okay, so we just need to make two disjointed subsets. Once we make two disjointed subsets, what happens is we take the first subset and we do a identity transformation. So this essentially is nothing but identity transformation. So we say x1 is equal to, we say z1 is equal to x1, we say z2 is equal to x2, we say z3 is equal to x3 up to zd. Okay. And then what we do is we take the subsequent d plus 1 to n z's, and we essentially scale it. Okay. So what we are doing here is that we are essentially taking this z and adding this neural network and adding the output of the neural network, which essentially takes your z I to d as the what you call the mapping. Okay. So sorry, this is not scaling, this is shifting. So what we are doing is we are shifting z. Okay. So what have we done? The key thing to note is you should be clear in your mind that I have taken my z's, I have divided it into two parts. They do not necessarily need to be equal. Okay. I have divided it into two parts. The first part I have done identity mapping. I have said that the first d z's are all equal to x1 to d. Same. X1 is equal, z1 is equal to x2, z3 is equal to x3, and so on and so forth. Okay. We took the next d plus 1 to n z's, and what we did was we shifted it by the output of a neural network, which takes the initial z's as the input. Okay. This is what we did. And obviously, since this is a very simple mapping that we are doing, you can see that obviously this identity transformation is invertible, and this is also invertible. Okay. The only thing that we need to do is calculate the Jacobian, and we are done. Okay. And the Jacobian of this particular matrix is essentially this. And you might ask me, let me see if I have space here. Yeah. So you might ask me, why is the Jacobian looking like this? The Jacobian is looking like this is because this Jacobian, I'm just writing it, this Jacobian will be like this. Okay. So I'm just writing it down. Okay. So this is what your Jacobian looks like. And what is this Jacobian doing? You can see that each of these entries in the Jacobian is, so it is saying that how does the first output change when you how does the first output change when you do a small change in the first input? How does the first output change when you do a small input, small change in the second input? How does the second output change when you do a small change in the first input? How does the second output change when you do a small change in the second input? That's what the Jacobian does, right? It's a n by n. Now, let's see what can we do with this particular, how does this Jacobian becomes that particular expression that we saw. So remember, here, your x1, sorry, your x1 to do is a 1 to d is a identity mapping, right? So this particular, when you take the derivative, this is actually nothing but identity. Okay. And if you see, this is an identity of d dimensions. Now, let's come to this. Okay. Top right. In the top right, you see that it is saying how does your first output change when you do a small change in the second input. Now you know from this particular thing that the second input does not even that the second input does not even depend on the second second output does not even depend on the second input. Okay, and that is why you see, so your x1 plus d does not depend on z d plus 1 by n, and that is the reason why this is going to become 0. Okay, and you can see here this is 0. Again, let me come to this first. What is this? This is basically the this is basically the bottom right. The bottom right, how can you write it? Expand it. You can expand it in this particular manner. Z d plus 1 n, okay, plus m theta. We have just used the function, and then this z d plus 1. Okay. Now here, if you see what has happened, your m theta does not depend on this particular thing here. So this particular thing here is cancelled. You are left with only you are left with only this particular thing. And if you see, this is what the expression is. Okay, this is this is what the expression is. Now, oh sorry, this is what the expression is. Okay, so what you are left with is identity. Okay, you are left with the identity, and this is the expression. So this becomes another identity, which is n minus d. And now we are left with only this. Okay, the bottom left. Now, what does the bottom left become? The bottom left again can be written like this, which is partial derivative of z okay. And when you take this particular thing, what happens? Now, you know, the derivative of this particular term with respect to this is essentially 0, right? And you are only left with essentially this particular term, which is your neural network taking this particular input divided by z 1 by d. And this is what it is. Okay. So now you can see here what has happened. The determinant of the Jacobian is the product of the diagonal. Now you have a unit matrix multiplied by another unit matrix. It basically becomes 1. And so if you use 1 in this change of variable, in this change of variable formula, if you 1 in this change of variable formula, it means that this particular term does not have any impact. It's same. All right. And that is why it is saying that it is a volume preserving transformation, since the determinant is 1. And what do we mean by volume preserving transformation? And how can we visualize it? We can visualize it in the form that your unit hypercube remains the same, but we can just move the probability mass here. Okay, it means that when you go from, let's say, this is a unit, let's say this is a unit hypercube, and this is your probability mass. What you can just do is you can move this probability mass across this hypercube, and that is what you can do. Nothing more than that, because it is a volume preserving and what you call transformation. All right. Now, the next step obviously is, if we do not, we would ideally like to not do volume preserving transformations. So The natural extension of this is to introduce. So what we have done is some shifting, and now the natural thing to do here is to introduce some scaling. Okay, so this is another version of this particular nice, where additive coupling layers are composed together, same as before. The final layer of nice applies a rescaling, which is this. All right, and this rescaling is also what you call invertible, and then you can, and basically you get the determinant is basically this, which essentially helps you uh, change the volume. So the thing to note here is that the additive coupling layers are stacked together to build the model composition, and since all have unit Jacobian determinant, the volume remains the same. We can only move the probability mass around. Now, to allow this model to scale the volume of the space, which is essential for our arbitrary representations or densities, we add this rescaling layer at the end, which helps us scale a little bit here and there, which makes it more flexible. Okay. Now, before I move any forward, any questions on these things? Yeah, Nisha, please go ahead. Nisha, your hand is raised. I'm not sure if it is by mistake. Okay. Anyone else has any questions?
Sir, I have two questions, sir.
Hello?
Yeah, go ahead.
One
Sir,
is,
am I
sir,
audible?
You are audible now, Nisha.
Oh, sorry, so sorry. Sir,
Yeah.
there is that slide for triangular Jacobian. Before that,
Hmm.
where we were taking log. So I just wanted to understand that. I
This
didn't
one, this one,
understand
this
that
one, this
properly.
one.
Yes, sir.
So, so what is your formula? This is your formula, right? This is the base formula.
Yeah.
Now, this is your likelihood, right?
Hmm. Hmm.
And you remember, we are not interested in likelihood, we are interested in log likelihood,
Okay.
right?
Yeah.
LL.
Yes.
Now, you put log likelihood on both sides. What happens? This is a product, right? And the
Yeah.
product becomes a sum when you
Some.
convert.
Yes.
Yeah, that's what it is.
So, sir, this P, yeah, this one, max log of. Can you
Hmm.
just little bit elaborate on this? Like,
Okay.
how did it come from there? Yeah.
So the the formula, the formula is this change of variable formula. Okay.
Yeah.
This this is the this is the probability density of a particular point, data point, right?
Yeah.
Now, when we are going into the likelihood space, what we want to do is we are not interested in the probability of a particular data point, but we are interested in the probability uh, of the entire data set.
Mhm.
Now,
Mm.
when you are doing the probability of the entire data set, this becomes like this. This D is essentially the entire data set.
Okay.
Okay, because when we are calculating the likelihood, what does likelihood say? Likelihood say what is the probability of the data given theta, given the model, right? That is the definition of likelihood. Likelihood says what is the probability of the data given the likelihood will tell you how basically what is the probability of the data given the model which is represented by theta. Now, when we have access to this likelihood, the way in which we train these models is using maximum likelihood, right? What we want to do is we want to maximize this particular term. Now,
Okay.
now, obviously, what we want what we want to do is when we are maximizing this particular term, an easy way for us to work is by using a log with it. because log is a monotonically increasing function. And what we can do is essentially we can put log on both sides. And if you remember your chain rule formula, your chain rule, the product becomes a sum.
Hmm.
Okay. And now it is easy for us to do all the calculations. And this is not specifically to normalizing flow models. This is general stuff. Okay. So we are
Mm-hmm.
interested in calculating the maximum log likelihood, MLE. Okay, the maximum
Yeah.
log likelihood estimation. Maximum
Yeah.
log likelihood estimation tells us how can we maximize the likelihood of the data given the model.
Hmm.
Okay, this is for
Yeah.
one particular point. And when we scale this up here, it scales to multiple, the entire data set. And since we have used log, we use a sum here.
Okay. Yes, sir.
Okay.
Thank.
No worries. Okay. Rajnish, you had a question, right?
Yes, sir. Sir, first is is this Jacobian is always a square matrix, sir? And in our case, what will happen if it is not a square? And
No,
second,
Jacobian will be a square matrix only if your input number of inputs is equal to the number of output.
okay, sir.
And in our case, in normalizing flow models, we said that X has the same dimension as Z, or Z has the same dimension as X, and that is why it is always a square here.
Okay, sir. So we are enforcing that it is square.
We
When
are
we are designing,
enforcing in design. We are enforcing in design. Otherwise, we cannot enforce the inversion.
sir. And second question is, sir, last slide we were rescaling layers. We were talking of nice. Sir. How we
Hmm.
identify the scaling factors for each dimension?
The scaling factor is learned. This is a learnable parameter.
So again, we have to implement some kind of neural network to learn this
we'll
effect.
have to we'll have to implement. So S is learned by the model one per dimension. So every dimension will have one scaling factor, and then we will have to basically learn those scaling factors there, and that essentially will give you the output.
Okay, sir. So my understanding is like if we are implementing nice, then we have a
Hmm.
neural network which is doing the transformation part, and there is another neural network which is learning the scaling factor part also. That's how it
Yeah.
will get
So
implemented.
so essentially you can and you don't need two neural network. By design, you can put it in the same neural network. This neural network will have a union of what you call parameters. Obviously, the theta will include this scaling factor.
Okay. Well, thank you, sir.
Any other questions? Okay. So let's move forward. So these are some of the samples that are being generated by NICE. I will not go through them. You can see that they are not bad. I mean, they are doing a pretty good job. This is quite a primitive network. All right. When I say primitive, I mean a few years back it has come up. All right. So now, obviously, the next question on that comes was we kind of used a workaround last time where we put a scaling factor at the end. And now what we want to do is we want to basically embed it in the network property. Okay. The way in which we'll embed it in the network is using an architecture called the real MVP. In real MVP, what happens is the first operation remains the same. This is identity transformation. The second operation changes a little bit. And in the second operation, what we are doing is we are in the, so you remember in here in the second operation, where is it? In the second operation, we were just basically doing this particular thing. Okay. Now here in this second operation, what we are doing is we are shifting. So we are shifting and we are scaling and basically does this. Okay. So your mu theta and your alpha theta are both neural networks, essentially, are both neural networks with parameters essentially theta, and it takes d inputs and outputs n minus d. Okay. So, and this is essentially nothing but a Hadamard product, which is essentially the element wise product. Okay. Now you can see that using this is also a, what you call, okay. This is also a invertible mapping. And you can see that if you do some algebra here, I mean, I'll not go through the calculation. If you do through the some algebra here, you will find that you can see that this is how the Jacobian looks like, and basically the final determinant looks like this. So this is a non-volume preserving transformation in general, since the determinant can be less than or greater than 1. Okay. So the only thing is that we have changed the architecture a little bit. We have, instead of, earlier we were just shifting, now we are shifting and scaling. And in the process, this is a invertible, this is essentially a invertible neural network. The only thing that we get in this particular thing, a little bit complicated structure, is this, right? Uh, I mean, this anyway, from the previous discussion as well, we are not even bothered about this. We are only bothered about this, okay, because we are going to take the product. And if you take the product, your determinant becomes this particular thing, and you are able to achieve this particular invertibility using this particular version of the NVP. Okay. Okay. Now, one particular concept that I need to tell you is something called interpolation. This is more of a diagnostic concept, and I'll tell you what exactly we do. All right. So, first of all, what is interpolation? And all of you may know it, but I'm still repeating it for anyone who does not know it. So it is essentially the process of estimating unknown values between two or more known values. So if someone gives you the temperature of today and someone gives you the temperature of day after tomorrow, and tells you that, can you predict the temperature of tomorrow? Or you will have to do some sort of interpolation. So that is general term interpolation. Okay. Now, in the latent space also, we can do interpolation. Okay. And what do we mean by doing interpolation in latent space? So see, whenever we are doing any deterministic transformation, every z is mapping to a particular x. So every z is mapping to a particular x. Now, obviously, we said that we are working in a continuous space. All right. So anything which is between z1 and z2 is something which we have not uh, evaluated, because we did not get the chance to evaluate it. It's a deterministic mapping. Okay. Now, if your probability distribution or your model that is giving your probability distribution or your latent space is good enough, if you sample something from in between, sample any z from in between z1 and z2, and this is just a hypothetical thing I'm telling you, z1 and z2, and if you convert it to that particular corresponding x, it should look and feel something between z1 and z2, right? For example, if you see this, you see many models and all those things, that you start with a female and then you suddenly kind of transition to a male, okay, with similar features and all those things. So we are essentially doing interpolation. Okay, so the typical thing, and this is one of the formulas that have been used in paper, but I'm giving you a simple version of the formula, which is, let's say we have 1 minus t z1 plus t into Z2, and where T belongs to 0 and 1. It's between 0 and 1. Okay. Now you see, as T moves from 0 to 1, the image should smoothly morph from phase 1 to phase 2 if this represents the phases. So that is what interpolation is doing. And why interpolation is necessary and useful? It shows that the model has learned a smooth and meaningful latent space, which is important. If we suddenly move from here to here and we see some noise coming out of here, then it means that the latent representation has not been learned properly. So it helps us also to understand how the model generalizes between the examples. And obviously, from a creativity standpoint, if you are able to do this, you even with this kind of deterministic model, you with interpolation, you can generate new faces, new images, and all those particular stuff. Okay. And the key thing to note here is that we essentially, during the training, there is no interpolation. Interpolation is a diagnostic tool. It comes during inference. All right. So interpolation essentially happens during inference, because we are trying to see whether how my model has trained and whether it is able to interpolate the images properly or not. So it tests essentially whether the latent space is smooth and meaningful. So we do small changes in Z. Do small changes in Z essentially create semantic changes in X. That's what we are trying to do. Okay. And so what this slide is saying is that with this particular model, the latent space representation is also good, as we can see using this particular form of interpolation. Now, any questions on this concept of interpolation? And this is not specific to flow models. Interpolation happens everywhere. Anytime you have a model where you are learning the latent representation, you can use interpolation as a diagnostic technique to essentially check if the unexplored spaces in the Z space are essentially giving you the right samples, right kind of samples.
So here in interpolation, we are actually assuming that the underlying distribution, the data distribution, is having smoothness.
Yes, absolutely. Bang on point.
Okay. So if in case we are having a distribution where smoothness is not there, then this interpolation might fail.
That is why this interpolation as a diagnostic tool is used to see whether there is smoothness in the distribution.
In the distribution. Okay. Thank you.
Okay. Now, so remember one thing, we talked about autoregressive models. In autoregressive models, we talked about that LLMs. So LLMs are essentially discrete autoregressive models. Now, what you need to understand is continuous autoregressive models are also kind of flow models. And why are we saying? If you see this particular thing here, now consider a Gaussian. Consider a Gaussian autoregressive model. You know this particular thing, such that P of xi is conditionally dependent on x less than n equal to I. And these are two neural networks which are here. So this is a Gaussian autoregressive model. How do you sample from a Gaussian, and can we repeat this architecture in case of flow models? Yes, we can. How? You see this. So here there was in the continuous autoregressive model, there was no concept of Z. Okay, there was only the concept of x and the random variables which were dependent, on which x was dependent, right? Here we are in a different zone where we are saying that we are essentially in a zone where we have x's and we have z's, and your x's are essentially dependent on z's. That's what we want to prove. Now, how do we sample from this model? We can sample from this model in this particular manner. Okay, so we can take z from a normal Gaussian distribution. Okay, and then what we will do is we will have two neural networks. We will have two neural networks, and those neural networks will output your mu and alpha. And using the reparameterization trick, we are going to put in the z here and essentially scale and shift it using the mu and alpha, and you get your x. And you repeat it multiple times here, and you are able to get multiple versions of x. So essentially, this is autoregressive model where you are trying to find one x at a time. First you sample z, first you sample z1, you pass it. Obviously, the first z1 will not need any neural network, but that's and you essentially find your x, and then you take your x1, pass it through your two neural networks, which outputs mu and alpha. And then those two, using the outputs of these two neural networks, you scale and shift your z, and you get your x2, and you do this particular thing multiple times. Okay. So essentially what is happening is, in this particular case, you had your um, um, model which was only dependent on X. Here you have a model where it is also autoregressive model, but it has that element of uh, essentially Z as well. So each time you are sampling Z, you are you are sampling Z, you are scaling and shifting the Z using the output that has come via the neural network. So essentially you take your Z, you get your first X, then you take your X, pass it through a two neural networks which output mu and alpha. Okay. And once you get your mu and alpha, you again sample Z2, you again shift and scale it using the output of the previous neural networks, and you get your x2, and so on and so forth. So you see, this is essentially a sequential process that we are doing. So it transforms samples from the standard Gaussian to those generated from the model, that is x1 and x2, via invertible transformations, which are essentially the neural network. Now, what is going to happen is this is going to essentially bring us to a very interesting topic, and we'll see how we are going to leverage this kind of architecture. Okay, this particular architecture is called the MAF, or the masked autoregressive flow. Okay, now, and you might be confused a little bit here when I'll show you two versions of it, but let me just tell you what exactly we are trying to do. So in MAF, we are trying to model the transformation from X to Z. We are trying to model this transformation. So if you, and you, when I'm talking through it, you just concentrate on this architecture. Okay, so you have a base distribution from which you sample Z, and you have a transformed distribution X. Okay, what we are trying to do, we are trying to model X to Z. So what will the neural network do? Your neural networks will essentially be take X as the input. Okay, and your alpha I is going to take, sorry, this is alpha, is going to take X. This is the input. Okay, so what are we trying to do? We are trying to map the transformation. We are trying to model the transformation from X to Z. For doing that, we pass X through a neural network and we get your alpha and Z. And then obviously we use your standard, you can use your standard reparameterization trick or scaling and shifting to basically get your Z's or whatever you want. Okay. So what happens here is during training, during training, all right, during training of the model, during training of the model, we know all our access. Okay. And so we can compute all the mu's and the alphas together. It's a parallel computation. Okay. However, during sampling, we must generate X1 and X2 sequentially because we do not know all the X's. Right? So what has happened here? The thing that has happened here is in the case of forward mapping, in the case of training, your training is fast, but your sampling is slow. Okay, your training is fast and your sampling is slow. And now you see what is going to happen here. So what this particular version here, is showing you how the inverse mapping is. This is the same MAF. It is the inverse mapping. And inverse mapping is going from X to Z. This is what we are modeling. Okay. This particular version is what we are modeling. This is the version that we are going to inverse. So when we model this, what you see is you have all your access together. You can basically calculate your Z's in parallel using this inverse transformation. Okay, but you have to, if you have to go the other way around, you are dependent on your access, right? You are dependent on your access. And you, during the generation time or the sampling time, you don't have the access in place. And that is the reason why, similar to autoregressive, and it is autoregressive model, you have to sample one X at a time and then move on to the other X, similar to what your LLM does. So in this kind of masked model, mask autoregressive flow, we are modeling the inverse mapping, which is fast, and the forward mapping, which represents sampling, is slow. Okay. And if we just reverse the role of X and Z, we get something called the inverse autoregressive model. The inverse autoregressive model is we are essentially modeling Z to X. So our neural network will take Z as the input. Okay. Now here, what is going to happen? During sampling, we can sample all the Z's together because all the Z's together in advance and compute this output of the neural network, right? Because we have access to all the Z's and we can sample together and we can basically compute this. So here the sampling is going to be fast. And similarly, now by this time, you know that the training here is going to be slow. Why? Because during training, we have all the access, but the Z's have to be computed in this particular manner using the inverse mapping. Okay. So the key difference between these two is that during training in IF, we are not sampling Z from the base distribution. Instead, we are computing Z from a given point X using the inverse transformation. Okay. So in these two type of architectures, which is MAF and IF, these are form of autoregressive models. But the only thing is that we have access to Z. And now what you will see here is in MAF, the training was fast, sampling was slow. Here in IF, the sampling is fast and the training is slow. And the only difference between these two models is the role reversal that we are doing. In case of masked autoregressive model, we are modeling this this particular what you call this transformation, that is x to z. Here we are modeling, where is it? Okay, here we are modeling z to x. So that is the key difference that we are doing a role reversal of x and z. They are mean the same thing. Z is still a latent variable, x is still the observed variable, but we are doing a role reversal in how we are modeling these particular things. Okay. And in this particular, with this particular, these two architectures, we see the drawback and the what you call the strength of these architectures. Now, this MF architecture, as you can see, masked autoregressive, and why it is called masked, because you are not able to see the forward. I mean, similar to autoregressive model, you are not able to see the future. Okay, so now this masked autoregressive model has the same properties as your typical autoregressive model, where your training is fast and your sampling is slow. This inverse autoregressive model has the opposite property, where your sampling is fast and your training is slow. Okay. Now, the key question that comes to our mind and why we have built this particular entire thing is, can we get the best of both worlds? Okay. And this will bring us to the next topic of discussion, which is called distillation. Okay. Now, any questions between in IF or MF? It should be pretty simple. MF is nothing but the autoregressive model. We are mapping X to Z. We are essentially mapping X to Z, and in IF we are mapping Z to X. It is the basically the inverse of a autoregressive model. Okay. Any questions? Okay. So that brings us to the next topic, which is distillation. And this was one of the groundbreaking work that was done by Google a few years back. And this is actually called the parallel wavenet. Okay. And in this particular thing, you have a teacher and the student model. Okay. Teacher is going to be parameterized by MAF, and teacher can efficiently can be trained using MLE. Once the teacher is trained, initialize a student model parameterized by IF, and the student model cannot efficiently evaluate density for external data point, but allows for efficient sampling. Key observation, IF can also efficiently evaluate. This point is important. So first, these 3 points needs to be clear in your head. Okay. What we are doing is we are using MAF. What does MAF do? MAF has the quality that it trains fast. And the drawback that we have here is that the sampling is slow. So what we do is we train a MAF, a simple autoregressive model. Okay. Once we train the autoregressive model, we will not use the same autoregressive model for sampling. Now you remember that IAF has this property that its training is slow, but the sampling is fast. So what we are going to do is we are going to use the strength of this and we are combining with the strength of the IF, and we are going to get a perfect teacher student model. So MAF is going to be trained, and then we are somehow going to basically use some mechanism to distill the knowledge of MAF into the student, that is IF, and use IF for sampling since sampling is fast. That is what it is trying. Any questions on this concept? Okay. Now, the key observation, one particular corollary that you need to be aware of is IF can also efficiently, we said that IF is not good for training, but IF can also efficiently evaluate densities of its own generations. If it has generated the stuff in sampling, it can easily, because it has access to all the access, it can basically um, 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 do the training very, and it can evaluate the densities, not training, sorry. It can evaluate the densities of its own generation effectively. Okay. Now the question comes is, how do we do the training? And these models, they are called distillation models. And the way in which we do the training is essentially using KL divergence. Okay, using KL divergence. And this is basically the expanded formula of KL divergence, nothing fancy. So this is essentially the KL divergence. And if you have to write it simply, this is basically minimize the KL of the IAF. This is the teacher. Okay. And this is basically, let me put it in the same MAF, and this is X. Okay. And if I have to just explain you simply, this is the student model. This is the teacher model. Okay. So what are we trying to do here? What we are trying to do here is we will sample from the student model. So the first thing that you have to note is my teacher model has already been trained. I have a trained teacher model now. Okay. Now what I need to do is somehow distill the knowledge of the teacher into the student and then sample from the student. That's the entire story. So what you have to do is first you sample from the student model, and this student model is still not trained. Okay. You sample from the X from the student model. And what you do is you first calculate the density of that particular point in the teacher with the teacher model. That is pretty easy. Your teacher model is already trained. It has access to the likelihood. Training is fast, and you can easily basically calculate the likelihood of this or density of this particular point. Okay. Now, the same point, we would also need to calculate the density via the student model. But we said that the student models are not good in training because the um, training is sequential in nature, right? It's slow. But at the same time, we said this particular point as well. IF can also effectively evaluate densities of its own generation. Here, the density is its own generation. We are calculating the density of its own generation, which it can easily do. Okay. And now your density calculation of the teacher model as well as the student model is fast. And what you are going to do is you are going to ultimately do nothing but minimize the KL. Okay. And as soon as you minimize the KL, you know that your student's model distribution is approximating well with the teacher model distribution, and your model is now trained. So you indirectly trained your student model, which was very slow in training, but now you have discovered a fast way of training using the distillation technique, uh, and using a pre-trained teacher model. And now that you have trained your student model, you can easily sample from it and you can do this stuff. Any questions? Okay, all right. So how do we, so this was basically from Google, okay? And how do we train it? Train the teacher model MAF via MLE, train the student model IF by minimizing the KL, and use the student model for testing or generation, whatever you want to do. And essentially, from a normal wavenet, the parallel wavenet showed around 1000x, 1000 times what you call improvement in and basically performance. Okay. Any questions?
Sir,
It, yeah.
does the distillation make the latent space much smoother?
That is more of a experimental point of view. I would not be able to exactly answer this question, Borij, right? I mean, there are various studies which have been done, but we'll have to do some literature review to give you an answer on that.
Okay, thank you.
Any other questions? Okay. So the next time someone tells you what are distillation models, you should be able to answer, because we have heard about distillation models a lot, right? In the market. So someone tells you a distillation model, you know what is a distillation model. There is a teacher student kind of thing where you basically distill the knowledge of the teacher into the student and then sample from the student. And the reason that we are using a distillation model in real time is because to get around with the what you call um, to get around with the drawback that some of our models are not I mean so, typical autoregressive models are fast in training but slow in what you call sampling. Okay, all right. So we have done good progress. And the last topic that I'm going to cover today, and then we'll probably end this lecture. I'll take any questions and then we'll kind of end this particular lecture, is essentially that the Gaussianization flows, something called the Gaussianization flows. Okay. So what is Gaussianization flows? Now, the concept of Gaussianization flows, this is also a flow model. The concept of architecture of a flow model, the concept of Gaussianization flows come from this particular discussion. So we know this is our mapping. So this is our mapping from X to Z. All right. Now, okay, so this is basically Z to X, right? So now what we want to do is let X is equal to F theta Z be a flow model with Gaussian prior. So your Z is Gaussian as we know. So this is your Z. This is a sample from Z. Okay. And this is basically the probability of Z. And let X belong to a true distribution P of data. Okay. So your Z is being sampled from a unit Gaussian. Your X is being sampled from basically the true distribution, which is P data. Okay. Now, flow models are trained with maximum likelihood to minimize the KL divergence between P data and P theta. Right? Ultimately, what we are doing is, if we know that if we are able to reduce the KL divergence between your true distribution and the model distribution, we are bang on target. Okay. And so the key thing here is that Gaussian samples transformed through P theta should be distributed as data. Okay. Now, what we can do here is that this scale divergence between your true distribution and your model distribution, which is P of X. So this is P tilde is your true and Px is your model. Okay. This is equal to, we can write it like this. Essentially, what we are saying is we have put in an inverse transformation on both sides. And we can say that this is also true, which is, I mean, these two are equal. And then we can easily write it like this. So what is the final thing that we have come up with? We have said that the KL of the probability of the inverse transformation of the samples from the true distribution and your Gaussian distribution, which is P of Z, should be equal. So now the trickery that has happened, you see what has happened. The trickery is essentially, we are saying that we know this particular P of Z. P of Z is essentially a Gaussian distribution. Can we say that the samples that we generate from the true distribution and we apply an inversion, they are also Gaussian in nature? If these things are true, so data samples transformed through the inverse transformation should also be distributed as the Gaussian. That is what we are trying to do. Okay, that brings us to the Gaussianization flows. Okay, now let's see the trick that they have applied. Let's start with a 1D example. Let the data X tilde have density P data. Now, when X has a density P data, we can also, it will also have a cumulative CDF of this, right? Now you look at this particular diagram. Okay, don't look at the formulas too much. Look at the diagram. This is your data distribution. Okay. Now, if your CDF, if your CDF is known, okay. Now you can basically approximate the CDF like this. Okay. This is your data distribution. This is your CDF. If you know your CDF, you can apply a Gaussian inversion on this CDF and make this a Gaussian. Okay. So what are we trying to do? It is trying to say that if F data is known, that is your CDF is known, we can sample P data via this particular thing. We can sample from X tilde from this particular thing. And we know that this um, and this has a uniform distribution. Okay, so that means that your u equal to this particular thing, this transformation, u is equal to the CDF of x is uniform. We know from statistic probability that we can transform a uniform into a Gaussian using the inverse of a Gaussian. And that is what we are doing. So the invertible transformation transforms your cumulative density CDF, which is uniform in nature, using a Gaussian transformation to basically Gaussianize the data. Okay. Now, let me show you an intuitive picture and probably it will be clear to you. Okay. So, and in fact, let me show you this picture. Okay, this is fine. So what we are going to do here is step one. The first thing that we are going to do is make each dimension individually Gaussian. So this is a two-dimensional data. This is dimension 1 and this is dimension 2. And what we are trying to do is, and if there are n dimensions, we'll be individually trying to basically Gaussianize each of the dimensions. So the first thing that we'll do is essentially make each dimension individually Gaussian. Okay, so we take each of the dimensions x1, x2 of our data and make it look like a standard normal or Gaussian distribution. How do you do it? We know the CDF, and we know that if we use the inverse of the Gaussian, apply the inverse of the Gaussian on the CDF, it turns into a Gaussian distribution. Okay, so every variable, this is x1, this is x2, every variable now kind of turns into a Gaussian. But the actual distribution, the multivariate actual distribution is still not Gaussian. It is still not achieved the Gaussianization. Only what is happening is you are at each step. The first step, you are trying to Gaussianize your individual dimensions, but your overall data, multidimensional, multivariate data is still not Gaussian in nature. Why? Because variables are still dependent. Okay, and this produces what is known as a Gaussian copula. Okay, it's basically a Gaussian marginals, but they are dependent. Okay, now this is step one. In step two, what you do, you apply a transformation like a PCA. Okay, what did PCA do? If you, and I'm just, it is not, you don't have to do PCA here, but you can do PCA here, and I want to emphasize on PCA because that will give you the true picture. What did PCA do? PCA took multidimensional data. Okay, and so that multidimensional data had variance. All right, it transformed it in such a manner that each of the principal components represented one dimension which has the highest variability. Okay, so, and it removed the dependency between the variables. Okay, so now here you see what you will do. You will apply a rotation matrix similar to a PCA to the transformed data, and what it is going to do is rotation preserves the Gaussian shapes. It does not change it, but they change how the dimensions depend on each other, similar to a PCA. So they can straighten out essentially some nonlinear dependencies, and after the rotation, the data becomes more independent. Okay. And now,
Hello,
when
sir,
you,
but
yeah,
sir, but PCA is not a transformation, it's a factorization.
It's a transform. PCA. What is PCA? So I'm just saying that this is somewhat like PCA. Okay, this is somewhat like PCA. So what does PCA do? PCA, you have some data distribution like this. It will move it like this, right? It does a rotation and it removes the removes the linear. I mean dependencies and make each of the axis independent. And this is somewhat doing here. It is applying not a PCA, but a PCA kind of rotation matrix where it is transforming the data. Okay. Now, what will happen is you repeat these steps every time. So every repetition forces marginals to become Gaussian. And then that rotation essentially reduces the correlation a little bit more. And eventually, what will happen is eventually when you do a sequence of these particular things, this is what it is going to reduce to. So you are going to get a Gaussian, multivariate Gaussian, and all these particular things are inverting. This is what is essentially the Gaussianization on Gaussianization flows. Any questions on this? So this is nothing but a different type of normalizing flow models. The entire thing that you remember is when we talked about normalizing flow models, we said by design they have to be deterministic and invertible. And here also they are deterministic and invertible. Okay, any other questions?
Any specific use case of this Gaussianization flows?
Specific use case of these Gaussianization flows, I mean, and see, any type of generative models, any type of generative models where you want to design and where you want to make um, transformation that is deterministic will be handled can be handled by Gaussian flows. All right. But when you say use case, see, these are actually, for example, that wavenet that I showed you, Google, that was basically at that particular time, it was used for speech processing. Okay. Now, each of these architectures, they are actually, they have been actually designed uh, by some doing some experiments, and for all of them the use cases might not be exactly known. Okay, so you may have to do some literature review to find out what use case exactly, where exactly they have used it, because everywhere I mean, not in all papers the use cases are mentioned explicitly in terms of where they have been used. So for example, just to tell you, transformers, when the transformer papers came out, uh, I mean, the specific in the paper, the specific use case was, I mean, which was mentioned. It was a very short paper, and the specific use case that was mentioned there was machine translation. Okay, but ultimately, where did it land up? It landed up in LLMs, right? Which is not a use case for this. But these Gaussian flows, you will have to do some literature review and see where these have been used in practice. I might not have the exact answer at this point of time.
Yeah, thank you, sir.
Any other questions? anything that you want me to repeat? We can go through anything from relational and autoencoder, autoregressive model, and any concepts that are not clear to you.
Hello, sir. Can you just quick recap of autoencoders and autoregressive sessions,
Okay.
like from a slides, so that we can have a quick refresh of those concepts, and if some doubt we can raise.
Okay. So see, it will not be possible for me to go through 50 slides in 30 minutes. All right. But I'll still see where how we can and do that. So you have to first ask, you have to first tell me where exactly you have the doubts. Just a moment. These are autoencoder. Okay. Now see, I mean, this is, I think there are at least the slides that I have gone through. I think there are at least 50 slides. So it's not possible for me to give a refresher at this point of time. I can talk you through the story of autoencoder, what exactly is autoencoder, or the other way we can do it is if you have any questions, we can and go through the questions.
Yes, sir. So, uh, with respect to the preparation point of view, what should
Mm,
like what we should cover, like in that sense, not exactly the specific doubts, but
mm.
uh, when we will be preparing for exam, what we should imposing, or what we should prepare for from these
Okay.
slides. Like,
So see, the important thing in, I think I have told you, I think I have told I think it is in this class or which class, I don't remember. So the thing that you need to do here is you need to understand how the story has evolved. Okay. So if a question comes that what are autoencoders, where I mean, and some conceptual question comes on autoencoders, you should be able to answer why is an autoencoder being used? What is the what is the encoder of autoencoder doing? What is the decoder of autoencoder doing? If you are asked about denoising autoencoder, what is denoising autoencoder doing? Why is it used? Why is it used? Okay. So the key thing here is concepts, conceptual understanding. You don't need to understand, you don't need to have the exact understanding of the mathematics that is there. But if someone asks you, for example, autoregressive models, if someone asks you why can't we use Bayesian network in autoregressive models, so you should have the answer of why Bayesian networks cannot be used in autoregressive model. Okay, why have we gone for neural networks? So the key thing here is that this particular subject is not a subject like machine learning or deep learning where you will have you can have, for example, decision tree questions and logistic regression, numericals, and all those particular things. This is a very conceptual subject. Okay, so if someone tells you that, for example, if someone tells you that um, uh, why in autoregressive model why is sampling slow? So you should have the answer of why is sampling slow.
sir, here can we just have an question from a sample paper, so that you can we elaborate that for a specific question, like how we should answer, or what would be expected there in the answer.
Do you have any sample paper with you?
Yes, I think we have received from announcement one sample paper.
Uh, Okay. So can you open the sample paper? Because I have not gone through the sample paper.
Sure, sir. I will get it.
Hmm. Can you tell me which announcement has the sample paper? Because there are so many. Can you tell me where exactly it is?
In ADL announcement, sir. It is recently, I think, given.
Uh, in this past question papers. These are past question papers. Is this the one?
Yes, sir. Yes.
See. Hmm. So this is a numerical, right? I mean, what is it saying? Consider a fully connected autoencoder. Each hidden node is connected to all inputs and outputs with two-dimensional one hot input and one hidden layer with ReLU activation function. Okay, and this is at iteration T, the weights are shown in the following autoencoder architecture with one hot this. All bias values are zero, assuming in learning rate is equal to this and momentum constant is equal to this. What is the activation function? Okay. So what activation function will you choose at the output? All right. Now, what activation function will you choose at the output? So this is you have a autoencoder. Okay. In the autoencoder, what it is saying, each hidden node is connected at all input and all output with two-dimensional one hot input and one hidden layer. At iteration T, the weights are shown to be shown in the following autoencoder architecture along with one hot encoded input vector. Okay, all bias are zero, assuming that the learning rate. So this particular question is, if you, what activation function would you choose at the output node? At the output node, the activation function that we usually choose is softmax. Okay, because softmax converts a logic into a probability distribution, and if you have a multi-class distribution, and you can basically uh, get get what you call the output of the classes, and this is essentially from here. Just a moment. Where is it? Okay, so see, this output layer has a logistic output, right? And an extension logistic, what will it will do? It is for binary outputs. And if you extend it to multi-class output, you can essentially put a softmax here, and you can and basically use this particular activation function. So that is what you will do here. What is the other thing? What loss function will you choose for training the autoencoder? Okay, what loss function will you choose for training the autoencoder? Now here we can see choice of loss function. So if it is if it is a regression on problem, we can use the mean squared error. If it is essentially uh, what you call a binary problem, a classification problem, we can use this particular function, which is basically cross entropy. All right. So this actually these are actually standard. So this is a conceptual question. What will be the value of the loss function at iteration t? What will be the weight W1 and W2 at t plus 1? And so this is something which you will just calculate and give it. Okay. Now, all right. So now these are the these question you will have to go through. So for example, calculate the inverse and determinant of this. Now considering transforming a uniformly based density this into this flow model, find an expression of the transform this. All right. So what it is saying, considering transforming a uniformly based density of z is equal to 0.1 using the function x is equal to f of z squared. All right. So this is the same thing. I mean, similar thing that we did here. Where exactly it is? This is the very first, I think first or second slide. So there was a function given and from x to f of x is equal to f of z. And it was said, what is f of z? F of z is equal to 4z. This is one example. And this is the other example, which was f of z is equal to exponential of z. And in that particular question paper, what it is given, it is z square. All right. You just have to use the change of variable formula and get the answer. Okay, what else is here? So this particular question is on calculate the inverse and the determinant. This is a standard stuff that you will have to calculate. And are the following functions invertible or not? Okay. So this is also something which you will have to test. You will have to test how whether it can be invertible. There are various tests of invertibility. You can just go through the test and you can check whether they are invertible or not. Okay. So once you know the test, you'll be able to answer all the three questions. And what are the advantages of pixel snail over pixel CNN plus plus? So that is also there in one of the slides, later slides. And assume the following made is used to this. X1 is the data value at time t and X1 arrives first, and this all nodes are numbering this. This is the mask autoencoder. Mask autoencoder also we have done. Mask autoencoder is here. Where exactly is the mask autoencoder? 3. This is the status. Autoregressive model. Yes. We said that these are autoregressive, autoregressive autoencoders. But why cannot autoencoders be autoregressive? Because autoencoders do not have any structure. To bring the structure, what we did was we introduced this concept, which is masked autoencoder for distribution estimation. And we explained in detail in terms of how the masking is done and how each of this is the algorithm. This is the algorithm for masking this this particular stuff here. We said how each of the layers will be masked, and this is the question based on this. So design all the necessary mask. So you have to design the mask here. Okay. What are the training parameters associated with the output node? So it's pretty standard stuff. The only thing is that you need to go through the slides and the concepts needs to be cleared. The only thing maybe when you uh, uh, you may have to deep dive a little bit is basically in terms of these numericals. In these numericals, you may have to just because numericals usually follow a pattern, and you may just have go through a few numericals from the paper, and they will be repeated. But these questions, all these questions here, this question here is directly from the slide. Okay, this question here, these are all from the slides. Okay. All right. So do one thing. What I'll suggest you all to do is uh, first open the previous year papers. All right. There are only few chapters which we are doing. The first important chapter is obviously the PCA. Okay. The second important chapter is autoencoder. The third important chapter is variational autoencoder is out of the scope. Okay. And the third one is the flow model. Now, what you have to do here is you remember one thing. If you have to stack these particular things, the easiest one is autoencoder. Okay. So go through the autoencoder slides, go through the autoencoder question papers. If there are any numerical questions from autoencoder, just practice those numerical questions because the pattern is going to be almost the same. And so autoencoder is the lowest hanging fruit that you will have. Then the lowest hanging fruit that you have is basically autoregressive models. The only difference between autoregressive model and the flow model, both are easy, but autoregressive model, I mean the um, it is the uh, theory is essentially very easy. The only thing that you need to remember is the different architecture, because there are a lot of architectures, and you just need to know which architectures are what and what is the strength and drawbacks of each of these architectures. And hardly there would be 8 to 10 architectures which would be there. And the trickiest part of this particular autoregressive models are essentially these architectures like MAID, because these MAID are very specific. You have to design the masks. You have to basically know how to design the mask algorithm to know how to design the mask. So these are things. Now, flow models, coming to the flow models, if you come to the flow models are actually a little bit easier than autoregressive models, because in flow model, the only thing you need to know is the change of variable formula. And this change of variable formula come in 2-3 flavors. One is the one-dimensional change of variable formula. One is the um, um, so you have the one-dimensional change in formula where your p of x at a particular x is equal to p of z of at a particular z into your basically the uh, derivative of h of x. Derivative of h of x, right? That was the simple formula that we just saw in the slide that I opened. Now, you need to know that particular formula. That particular formula is the one from which the question came. But at the same time, you should also go through what you call the other versions of the formula, which is essentially using the determinant of the Jacobian of the inverse. Okay. And while the name seems complicated, but Jacobian is nothing but essentially the gradient of all the outputs with respect to all the inputs. Okay. So if you know this change of variable formulas in your flow models, any numerical that is going to come you should be able to answer that particular numerical. And the only other thing is you can see which function is invertible or not. There are various rules about it. You can just go through it. The second part of the flow models, which is essentially IF, MF, distillation, Gaussian flows, they are more conceptual in nature. Okay, so typically the question may sound a little bit tricky, but ultimately when when it will be the crux of the matter when it will be asked is maybe why do we want to use IF in a distillation model? Okay, and you need to know what is a why are we using MF? What are the strengths and dependencies of MF? What are the strengths and dependencies of IF? And how do we distill the model? And that brings us to basically to answer that particular question. So after PCA, after your autoencoder, you should actually go through your what you call flow models. Flow models is easier, and then you should or basically target your what was the autoregressive models. Autoregressive model, the only thing is that you need to go through the various architecture, know why is one better over the other. And that may take a little bit of time because there are quite a few models. And lastly, you go through PCA because PCA is a little bit tricky. Okay, and this is based on my experience. Your stacking order may be different, and but this is how you should essentially uh, tackle this particular thing. Okay,
Sir, one
so
question:
yeah,
does
yeah.
VA? You said that VA might not come to the mid-sem, so
VA is not in the VA is not in the syllabus. You just confirm with the has anyone given you the syllabus?
no.
No, right? So VAE has not been completed in other classes. I'll just show you where exactly is VAE. So if you go through this, VA is actually after this normalizing flow models. So what we have is still normalizing flow models. So you have your PCA, autoencoder, autoregressive model, normalizing flow models, and then we'll have VA in the this. But I wanted to cover VA because without VA, I always feel that, I mean, it doesn't make sense to go through normalizing flow models of why exactly we are using normalizing flow models. But that is exactly so you don't have to go through VA.
Okay.
And in fact, in the question paper, past question papers, you have seen that there is no VA questions.
Okay.
All right, then let's close the class for today. We'll catch up after uh, your exams and we'll start with GANs. Right? Thank you so much.
Thanks, sir. Thanks, sir.